this tutorial, we're going to look at how to fit a simple linear regression model. The example we're going to use throughout this tutorial sequence is described on the previous web page, but to briefly review what we're doing, essentially we're going to examine predictors of hospital ratings using publicly available hospital-level survey information from data.medicare.gov. Now, one of the key terms in that sentence is we're looking at hospital-level data. So the unit of inference that we're going to be using, it's hospital level. So the two covariates we're going to examine in this lab exercise, the explanatory variable is nurse always. And this is the percent of patients in a hospital who said their nurse always communicated well. So nurse always, it's a percent. Additionally, our outcome variable is recommend yes. And this is also a percent. It's the percent of patients who would always recommend the hospital. So these are our two variables, and we want to examine whether there's a linear relationship between these variables. Anytime you want to do a linear regression analysis, it's always good to go back to what we've already done and first make a scatter plot of these two variables to look at the relationship between them, and then go ahead and calculate the Pearson correlation coefficient. So go ahead and open up Stata and we'll go through that. So I've opened the hospital data dataset. The first thing I'm going to do is make a scatter plot. Now the y variable I'm interested in is recommend yes. That was my outcome. The x variable is nurse always. Go ahead and hit submit, and we see a scatter plot of the explanatory variable versus the outcome. Looking at this scatter plot, it's pretty clear that there's some linear relationship between these two covariates. Let's go ahead and calculate the Pearson correlation coefficient. Recall that to calculate the correlation coefficient, we go Statistics, Summaries, Tables, and Tests, Summary and Descriptive Statistics, and click on Pairwise Correlations. The variables I'm interested in are recommend yes and nurse always, so I plug those into the variables window and hit OK. I find that the correlation between these two variables is 0.66. So it does appear that they are positively correlated. However, simple linear regression has the advantage of we can better quantify the relationship between these two variables and come up with a more intuitive measure of the relationship between these variables. We can make statements such as, for a 1% increase in the percent of patients who say their nurse always communicated well, we would expect on average to see a corresponding, say, B% increase in the percent of patients who would always recommend the hospital. And we can estimate this B that I've thrown out there, just a random variable, say B. We can estimate that guy by fitting the appropriate linear regression model to come up with some intuitive measure of this relationship. So let's go ahead and look at linear regression. First thing I want to do is try to articulately state the model that I'm going to be fitting. So I'm going to define some notation first. Our outcome is yi. And it's defined as the percent of patients in hospital I who would always recommend this hospital. I'm just indexing it by I so that we can keep track of the hospitals. So we'll say there's I equals 1, 2, all the way up to n different hospitals, where n is the total sample size. Now my explanatory covariate is going to be x. X is defined as, again, the percent of patients in hospital I who say that their nurse always communicated well. Now, given this notation, we can go ahead and write down our linear regression model. We say that our outcome yi is equal to alpha plus beta times xi, our explanatory covariate, plus some residual error. And we model this residual error as following a normal distribution with mean 0 and variance sigma squared. Now the goal of linear regression is to go ahead and estimate alpha and estimate beta so that we can quantify the relationship between xi and the mean of yi. Now, rather than writing this model in terms of those residual errors like I did, we could write down an equivalent linear regression model by modeling the mean of yi given our covariate. So essentially what we do is we look at the expected value of yi given the covariate value, and we say that that's equal to alpha plus beta times xi. And now, rather than dealing with the residual errors like we saw before, what I can say is that my outcome yi follows a normal distribution with mean equal to this mu and variance equal to that same residual variance sigma squared. This is an equivalent way to write the model. So this is just for you to know, because if you see these two different model formulations, you'll now know that they're doing the exact same thing. All right, so now that we've stated our model, let's go ahead and look at the assumptions required to fit a linear regression model. In linear regression, there's four main assumptions that we make. The first one is that we have independent observations. In our case, we're dealing with just a survey of many hospitals. We can assume that these hospitals are independent of each other, and so it seems reasonable to say that we have independent observations or independent hospitals. Next, we need to assume that there's a linear relationship between the outcome and covariate, and we looked at the scatter plot, and this looked pretty reasonable. The next two assumptions are the ones that are a little bit hairier to try to interpret in practice, but we can do it. The first is that yi given xi, so the outcome given the covariate, is normally distributed. The next assumption we need to make is homoscedasticity. And this is just a very long word that means constant variance. So the variance of the outcome given the covariate needs to be constant, regardless of what the value of the covariate is. So we'll go ahead and look at a scatter plot again to see if homoscedasticity and normality appear to hold in this instance. So the normality assumption says that for any value of x, that my outcome y should be normally distributed, so that these observations for this value of x, these guys in here, they should follow a bell curve. Now, we can never exactly evaluate that observation, but as long as we don't see any crazy outliers or anything weird going on, generally, in our case, this normality assumption appears to hold. So we could draw little bell curves showing that our outcome appears to be pretty normally distributed for any value of x. My bell curves aren't very good, but hopefully you get the point. Now the next assumption we made was constant variance. And the way that I like to assess this, or eyeball it, is that we can draw this linear line through there that looks pretty linear, and then along the outside we see that the amount of variability, it appears to be pretty constant. We don't see anything odd going on. One example might be if my variance increased with x. So if I could draw some sort of fan pattern out here, and if I saw a bunch of observations here, that would be an example of the variance increasing with x. But since these lines appear pretty constant, it looks like we see that homoscedasticity holds in this example. All right, so now that I've finally decided it's okay to fit a linear regression model, let's go ahead and do that in Stata. We go Statistics, Linear Models and Related, and click on Linear Regression. The dependent variable is recommend yes. The independent variable is nurse always. So when I run this regress command in Stata, with recommend yes as my outcome and nurse always as my covariate, I end up with a bunch of information from Stata. So let's go ahead and try to make sense of what Stata gave us. First of all, this underscore constant, that is alpha from our model. That's our constant in the linear regression model. And then nurse always, that's the name of our explanatory covariate. So what that guy corresponds to is it gives us the information for beta. So using all of these pieces of the puzzle, I can write down my fitted regression line as yi is equal to I can write down my fitted regression line as yi is equal to my constant alpha, negative 19.2, plus beta, which we saw as 1.16, times the covariate value plus some residual error. And remember, we said this residual error follows a normal distribution with mean mu and some variance sigma squared. If I look up here where it says root MSE and stata, this number gives you the value of sigma because it's the root MSE. So if I wanted to know sigma squared, it would just be 7.28 squared. So now I have my fitted regression model. These are all the pieces of information I need to know to completely characterize my fitted regression line. Now let's go ahead and interpret the parameters from our regression model. First, let's look at beta. I see that a confidence interval for beta is 1.12 to about 1.20, shown right here. And I can interpret beta as follows. For a 1% increase in my covariate xi, so for a 1% increase in percent of patients who reported that their nurse communicated well always, the corresponding increase in the percent of patients who would always recommend the hospital is 1.16 on average. And the key thing to talk about when we're interpreting beta is it tells us about the behavior of our outcome yi on average. So really, it tells us about the expected value of yi given our covariate. So that's how we would go about interpreting beta. Next, let's look at alpha. If we think back and remember that the expected value of yi given xi is equal to alpha plus beta xi, then think about it. If we plugged in 0 for xi, then this term's going to cancel out. And essentially what alpha is it's the mean value of the response, yi, when we fix the covariate to 0. Now if I summarize the nurse always variable, I find that this variable for any given hospital, it only varies between 48 and 98. So there aren't any hospitals that have xi equals to 0. That doesn't exist in our data set. In fact, the minimum value of xi is 48. Therefore, in this case, alpha really has no meaningful interpretation in practice. It's just a tool that we can use to predict other values of the mean of yi, but it doesn't, in and of itself, it's not meaningfully interpretable. The reason for that is we really only know the behavior of the expected value of yi for values of x that range between 48 and 98. So it doesn't make sense to assume that that linear relationship holds for values of xi that are outside of the range of our covariate data. So we can't extrapolate beyond the range of our covariate information. This is a very important aspect of linear regression that you always need to keep in mind. We can't extrapolate beyond 48. All right, let's go back to our interpretation of this regression output. The next thing I want to do is I want to test the hypothesis that beta is equal to 0 versus the alternative that beta is not equal to 0. And the way that I do that is I focus on this line right here that contains all of this information for beta. I find that beta hat is equal to 1.16. Find that the estimated standard error of beta hat is equal to 0.02. which leads to a t-statistic of 52.19. Now I know that under my null hypothesis that my t-statistic, this guy follows a t-distribution with n-2 degrees of freedom. And I see up here that my number of observations is 3,570. So it would be 3,568 degrees of freedom. And this corresponds to a p-value that's very small. My p-value is less than 0.001. And therefore, I would reject my null hypothesis and conclude that the percent of patients who say that a nurse always communicates well is positively correlated with the percent of patients who would always recommend a hospital. Next, to examine the amount of variability explained by my covariate, I can look at the R-squared. For this model, my R-squared is equal to 0.4329. R-squared is known as the coefficient of determination, and in this example, it tells us that 43% of the variability among the observed values of recommend yes, the outcome, 40% of that variability is explained by the linear relationship with nurse always. The remaining 57% of the variability is unexplained, implying that there are other factors that contribute to whether the percent of patient. The remaining 57% of the variability is unexplained, implying that there are other factors that contribute to the variability in this recommend yes outcome. Another way we can look at the fit of our model is to use a residual plot. So after you fit a regression model, Stata stores some information, and you can use diagnostics in Stata to go ahead and look at the model fit. To do this, I go Statistics, Linear Models, and Related, and then I go to Regression Diagnostics right here. First thing I want to look at is the residual versus fitted plot. And I can just hit OK. And it makes a plot of the fitted values of the outcome versus the residuals for those fitted values. And what I'm looking for here is I don't want to see any trends in these residuals. I see that they're about mean 0. I don't see any weird trends going on. If I saw any, U shapes or, the residuals getting larger over time, these would be problems. So as long as you don't see any patterns in that residual plot, that means your model's probably doing okay. Another plot we can look at under linear models and related regression diagnostics is this residual versus predictor plot. So I can look at the residuals now as a function of the covariate in the model. And again, I don't see any major trends in this residual plot. Things look okay. So I can assume that the fit of my model looks okay. I don't see any major outliers. I don't see any weird trends in my residuals. However, there's really typically never a definitive answer to whether your model fit is good. I'm sure I could add more covariates to this model to improve my fit, and we'll do that in upcoming tutorials. It's always important to keep in mind that modeling is both an art and a science, and that's the artistic form really comes in when we're thinking about, does our model fit well? Could I improve this model? The next thing I want to do is I want to predict the expected percent of patients who will always recommend the hospital when the percent of nurses who always communicate well is 80%. And I want to construct a corresponding 95% confidence interval for that. So what I want to do is I want to look at the average value of yi when xi is equal to 80. And the way that I can estimate that guy is I can say this is equal to alpha hat plus beta hat times, and I just plug in 80 for xi. And if I do that math, you find out that the answer is 73.6. The easier way to do this in Stata is right after you fit a linear regression model, you can use the lincom command. And what that's for is it's for linear combinations of your covariate. So what I can say is I want to do alpha, which Stata defines as this underscore constant, plus beta, or just the name of my covariate, nurse always, times the value of that covariate, which is 80, and hit enter. And again, I see that the predicted value of the mean of yi when xi equals 80 is 73.54. Now it also gives me a 95% confidence interval value for the expected percent of patients who always recommend the hospital. So my 95% confidence interval for this mean is 73.3 to 73.8. Now this tells me on average what happens at hospitals where 80% of the patients report that the nurse always communicated well. A very different but related question would be, suppose we have a new hospital that we don't have data on recommend yes, but I'd expect that this hospital has 80% of the patients reporting that the nurses always communicate well. Now for this new hospital, I want to predict the percent of patients who always recommend the hospital, and I would want to construct a corresponding 95% confidence interval. Now to think about this, we have to think way back to week 5 when we looked at confidence intervals and predictive intervals. Essentially now we're looking at a predictive interval, and we're looking at a predictive interval for one new observation where we know that 80% of the patients report that the nurses always communicate well. So I want to predict this new observation. Let's call it y tilde, given xi equals 80. Now my best guess for yi should be the mean when x equals 80, right? And we saw before that that mean was 73.6. So my best guesstimate for this prediction for the new hospital would again be that 73.5% of the patients would always recommend that hospital. But the most important thing is now, I want some measure of uncertainty associated with that prediction. What's a plausible range, a 95% confidence interval for this prediction? And we saw in class this week that to get that prediction, essentially what we have to do is we have to look at the variance of the mean of yi, so the mean when x is equal to 80, but then I also have to bring in that residual variability, that sigma squared hat that tells me that for independent hospitals, what amount of expected additional variability do I expect to see other than that explained by x. So this represents the variance of my new prediction. To get the standard error of that prediction, I can just take the square root. So to do this in Stata, I can take the standard error of the mean, which is shown in that lincom command, square that, go back and find my root mean squared error, the 7.2804, square that. That would give me an estimate of the variance. To get the standard error, I would take the square root, and I find that the standard error of my new prediction is 7.28. So to get a 95% confidence interval, what I would need to do is I would need to take my y bar plus or minus the value of the t-distribution with 3568 degrees of freedom times the standard error, 7.28. To find the appropriate value of the t-distribution, remember we use this inverse t-tail command, 3568 degrees of freedom, and we want the 0.025 quantile because it's the inverse t-tail command, times 7.28. And I get the lower bound. If I change the minus to a plus, I get the upper bound. So I find that my predictive interval for this new hospital is now 59.2 or 59.3 to 87.8. And this interval is a lot wider than the intervals that we saw when we predicted the expected value of yi when x was equal to 80. That interval was only 73.3 to 73.8. So the point of this is that when we're talking about means, when we're talking about averages and large samples, we can get this really tight bound for predicting the mean, assuming our linear regression model is correct. But if we take a new observation, a new hospital, and we want to predict what happens at that one specific hospital, we're moving from talking about means to moving to talking about individual predictions. And when we deal with these individual predictions, we have a lot more uncertainty.